As a fun side project, I was thinking of building a small audio amplifier. In this video, I'm going to walk you through the whole process, including how I solved some of the most annoying issues you're bound to run into when building a circuit like this. So let's get started. I got this 12-volt switch mode power supply. It's rated at 2.5 amps, so that should be plenty for a small amp. I've got some refurbished speakers that I've already housed in custom 3D printed enclosures. Let's dive right into it and start with the basic amplifier circuit. So the basic circuit of an audio amplifier is quite straightforward. There's an input. I would like to use 2 op-amps to amplify the signal. And we've got an output stage to drive the speaker. This consists of 2 transistors. This is the NPN one and this is the PNP transistor. So this is the basic circuit of a class A/B amplifier. And this is the speaker. I've got a 12-volt power supply. So it means the audio signal has to fit between the 12 volts and ground. And the op-amps are not able to operate all the way up to 12 volts or 0 volts. They need a margin of 2 volts at either side. So the maximum swing the signal can have is 12 minus 2 times 2 is 8 volts. So the maximum output signal we can have is plus or minus 4 volts. The op-amps amplify the voltage and the output stage amplifies the current. So at this point we've got maximum voltage of 4 volts. Let's say we would like to amplify even low level signals as low as 150 millivolts and to amplify them to the fully extent of what the amplifier is capable of. So that's a gain of 4 divided by 1.15 and that's a gain of 26. So let's round that up to a 30 to make calculations easier. We can divide this gain over these 2 op-amps. Setting the gain of an op-amp is quite straightforward. There's an input resistor R1 and a resistor R2 in the feedback loop. The gain of an op-amp is given by R2 divided by R1. So it's quite easy. If you want a gain of 3, let's take a 10k ohm resistor for R2 and a 3.3k resistor for R1. And it equals a gain of 3. So it's the same for the second stage. I want a gain of 10. So let's take a 20k ohm resistor in the feedback loop and a 2k ohm resistor at the input. 20k divided by 2k equals a gain of 10. So in total it has a gain of 3 times 10 is 30 and that is exactly what we were aiming for. There's one last thing to say about this circuit. The signal swings between 12 volt and 0 volts up and down around a virtual midpoint. This midpoint is of course 6 volt, but it has to be set at the input of the op-amp, so the op-amp can use it as a reference. And because it is used as a reference, it needs to be as stable as possible, just like the 12-volt power supply. But we will dive into that later on. First, let's put this circuit on a breadboard, put some signal into it and see how it performs. To put it on the breadboard, I first drew up this schematic. This is the 12-volt power supply. The VCC is the main power rail to deliver supply voltage to the different stages. The 6-volt reference voltage is created by using a voltage divider network. This reference is connected to the op-amp inputs. This is the first stage, this is the second stage, and this is the output stage. And of course we've got the speaker. So I put it on the breadboard. We need the power supply of course. Well, these are the 2 resistors making up the voltage divider network. These are the 2 op-amps in a single package. This side is the first stage and this side the second. These resistors are R1, R2 and R3, R4. So these are the power transistors for the output stage. The two 5-watt emitter resistors, they are needed to prevent thermal runaway of the transistors. And we got a capacitor at the output, just as at the beginning, as the signals inside the amplifier run at the 6-volt DC level, and we don't want that voltage at the speaker or the input device. The caps prevent that from happening. So let's take a look how this circuit performs. I've added this multimeter to keep track of the amps going into the amplifier. And let's hook up my signal generator to put in a sine wave, and let's connect the oscilloscope to the output so we can see what this circuit does. Okay, this purple sine wave is the 1 kHz input signal and the yellow line is the output. Let's turn it on and see what we've got. Oh wow, this is chaos. There's not even a hint of a sine wave in the yellow output trace. As you can see, the circuit is so unstable that even the input signal is affected. Let's check the output of the second stage. Not good. And the first stage, also not good. Let's check the reference voltage. Wow, this is very unstable and absolutely unusable as a reference. This problem is the first that needs fixing, I guess. So the reference voltage is the problem. It's not stable. The voltage divider has two 100k ohm resistors, so there's only a little current flowing through it. In theory, the op-amps in the amplifier do not draw any current, but in the real world, they can draw up to 800 nanoamps each. An extra current of 800 nanoamps or more can disturb this voltage divider quite easily. So, the way to fix this can be by, for example, lowering these resistor values. Or one can use a 6-volt Zener diode or a 6-volt voltage regulator, all making this reference voltage much more stable. But I'm choosing another op-amp to stabilize this reference voltage. One thing I like about using an op-amp is the reference voltage will always be the midpoint. So if I choose a higher voltage power supply, the midpoint will rise with it. So using a Zener diode or a voltage regulator will keep this reference voltage at 6 volts, even if I use another power supply. So using another power supply will not get me a much more headroom for my signal swing. So how does the circuit look if I put in this op-amp? Well, I've drawn it here. I lower the resistor values of this voltage divider. So there's 10 times more current going through it, but still well below 1 milliamp. So it's nothing to worry about, but it makes it harder to disturb if there is some current drawn by this op-amp. The only op-amp drawing current from this voltage divider is this one op-amp, and not all the 4 op-amps used in the amplification of the signal in this amplifier. So as I showed earlier, the gain of an op-amp is defined by the input resistor and the feedback resistor. In this case, it equals to 1. So we've got a 6-volt reference voltage. The op-amp can provide a lot more current than a voltage divider could do. So in theory, this would give us a much more stable reference voltage. So let's take a look how it performs if I put this on the breadboard. So I put this buffer circuit on the breadboard, the voltage divider, two 10k resistors, and this buffer circuit provides a stable reference voltage for other parts of this amplifier. So let's take a look how it turns out on the scope. We can see the pink input signal. Let's switch it on. Well, the output signal has improved quite a lot. You can clearly see it's a sine wave. Let's hide the input signal so we can clearly see what the output signal looks like. As you can see, it's a nice sine wave. However, there are a lot of spikes cutting through the sine wave, and that's not good. And this is also a power supply issue. So let's dive into that next. So let's take a look at the noise in the power supply. I connected the oscilloscope directly to the output of the power supply. It's a switch mode power supply, so it leaves its mark in the DC output. I'll turn the scale down a bit. As you can see, these are exactly the spikes we saw cutting in the output sine wave of the amplifier. And this is generated by the switch mode power supply. To use such a power supply in an audio amplifier, we have to get rid of those spikes, obviously. One of the ways to do that is to add another capacitor, like the one I've got here, 2200 microfarads. So let's take a look what will happen at the oscilloscope if I put in this capacitor. Wow. As you can see, that removes more or less all the spikes. Let's zoom in a bit. Well, we can clearly still see some of the distortion, but the level is way down. The peak to peak is 8 millivolts. The RMS value of this distortion is well below 1 millivolt. So that's quite good. I would say this is probably good enough for the amplifier, but so let's see if we can cut it down a bit more. Well, now we're at it. One of the things to take into account is the position of the capacitor. I've placed it here quite close to the output of the power supply and close to the probe of the oscilloscope. Let's take a look if I place it farther away, like so. You can clearly see the distortion is much more visible if I place it further away from the power supply. Let's take, for example, this side, where you can see it has almost no effect on the level of distortion. The further away you position it from the power supply, the less effect it has on the level of noise. Let's put it back close to the power supply and you can see this is, well, quite good. So one of the things we can do to improve the noise reduction is to add an inductor, also called a choke. If we put that on the output of the switch mode power supply, it will block some of the high frequency components. Together with a capacitor, it forms a low pass filter, and if these values for this inductor and capacitor are chosen high enough, it will block out almost all frequencies and leave a very clean DC. So let's see what happens if I put this in. At the moment we've got around 10 millivolts of distortion and you can still see some of these spikes. Let's see if it improves if I'll put in the inductor. Okay, I will switch this over here and put the inductor in like so. Well, that's no improvement obviously, but let's add this capacitor. Well, it's not a large improvement. As you can see, the noise is more random and the average value has dropped down a bit more. So we can use it this way for this audio amplifier. So let's see what happens to the output if we put in a sine wave and use this power supply where we have reduced the noise quite a lot. So let's take a look. So let's hook up the oscilloscope at the output. All right, look at that. That's a clean sine wave. So I think that that takes care of the power supply. We've got a very clean sine wave at the output. So let's take it to the next step and see how this amplifier performs if we hook up a speaker, or in this case a dummy load of 4 ohms. Let's see how it holds up. I updated the schematic. I put in a 1 millihenry inductor and a 2200 microfarad capacitor. So the power supply is stable enough for the audio amplifier, and we just saw on the oscilloscope that the output sine wave looks very clean, but that's only the output of the voltage amplifier. As I showed earlier, these two op-amps take care of the gain of the voltage, but to drive a speaker we also have to amplify the current. And this last stage is the current amplifier. So we have seen on the output that the amplification of the voltage is doing great. Let's take a look how the current amplifier performs by putting a load on the output. I've got this 100 ohm power resistor. It's a bit more than the 4 ohms of the speaker, but I do not want to stress the output stage that much at the moment. First, let's see how it performs. We've got a nice sine wave. Okay, so when I put a 100 ohm resistor on the output, let's get rid of the original signal. We immediately see the crossover distortion. As I explained earlier, this is a class AB amplifier. That means there are 2 transistors working together to amplify the current in the output stage. This is the NPN transistor and it amplifies the positive half of the sine wave. And this is the PNP transistor and it amplifies the negative half of the sine wave. At the crossover point at 0 volts, these two should have a nice handover of the signal. At the moment that is not the case. As you can see, there is a point at which the PNP transistor is already switched off and the NPN transistor has not switched on yet. So there's a dead zone here at the crossing of 0 volts. That's a problem obviously, so how do we get rid of this crossover distortion? So the advantage of a class AB amplifier is the transistors are switched on only half of the time. It is more energy efficient than using one transistor that has to be switched on all the time. The drawback is that you have to handle the crossover point. Let's explain what's happening. To switch on this transistor, NPN transistor, there has to be a voltage drop across the base and the emitter of around 0.6 volts. At the PNP transistor, it's the same. The voltage drop across the emitter and the base has to be 0.6 volts. So if a sine wave arrives at this circuit, the first 0.6 volts will not get amplified as the transistor is not switched on yet. The same holds for the negative 0.6 volts, as at this point the PNP transistor will not have switched on. So the output will look like this, just what we saw on the oscilloscope, where the part between the 0.6 and the minus 0.6 is not amplified at all. So we have to come up with a solution to create a nice handover point at which both the NPN transistor and the PNP transistor are switched on slightly at the handover point. So there is no crossover distortion. To do that, we need to create a voltage drop of 1.2 volts between the two bases of the transistors. We can create such a voltage drop of 1.2 volts by using a resistor, for example. Connecting this to ground and connecting this to the VCC. We could calculate this voltage divider network and make sure there is a voltage drop of 1.2 volts across this resistor. That's one way. Let's put it on the breadboard and see if this theory holds up in real life. So I added a variable resistor, a potmeter, between the base of the NPN transistor and the base of the PNP transistor. As you can see, we still have the same kind of distortion we had before. Let's increase the resistor value and see what happens to the crossover distortion. As you can see, the crossover distortion disappears if I turn up the resistor's value. But be careful, because as you can see here, the current is going up, which is quite logical as both transistors are switched on. But if I set the resistor value to high, the current will explode, as will your transistors if you're not careful. Because you switch on the transistors fully, and they eventually turn into a short circuit. You have to be quite precise to set the voltage drop between the two bases of the NPN and PNP transistors. Fortunately, there's a pretty good solution to do just that. The preferred way to deal with this crossover distortion is to use a circuit that's called a VBE multiplier. Let me show you what it does. The main element of this circuit is also a transistor, as it has the same characteristics as the transistors in this output stage. The voltage drop across this base emitter is also 0.6 volts. If we can multiply that by 2, we've got exactly the voltage drop we need between these two bases. So how do we achieve that? Let's say I'll put this resistor between the base and the emitter, and I'll put this to the power supply. The voltage drop across this emitter will be exactly the same as the voltage drop between the base and the emitter. I'll tell you why. If this voltage drop is lower, like 0.3 volts, the transistor is turned off, as this voltage drop is too low for the transistor to turn on. So there will be no current flowing through this part of the circuit, only through this part, resulting in a higher voltage drop across the resistor. But if the voltage drop is going higher than 0.6 volts, the transistor starts conducting, lowering the voltage drop across this resistor. So it will result in a stable voltage drop of exactly the voltage drop across the base and the emitter. So how do we multiply it by 2? That's by putting a resistor between the base and the collector. As we know, the current flowing through the base of a transistor is very small. So we can assume the current flowing through this resistor is the same as flowing through this resistor. So if we take a 1K resistor here and we take a 1K resistor here, the voltage drop over this resistor is exactly the same as this resistor. So we get a 0.6 volt voltage drop as well. In this way we create exactly the voltage drop we need between these two bases, and it has the same temperature characteristics, meaning the voltage drop will go down when the components heat up, because this transistor has similar characteristics as these transistors. Let's see how it looks if I put this on the breadboard. So I updated the schematic once again. As you can see, I put in this VBE multiplier between the two bases of the output transistors. As you can see, I replaced the resistor between the collector and the base by a smaller resistor and a trimmer. So I can set it exactly the same as the resistance value between the base and the emitter. So let's take a look at the scope what we've got at the moment. You can see there's still a small crossover distortion. Let's see if we can zoom in a bit. By adjusting the trimmer, what I'm going to do now, by turning up the resistance value, I can, as you can see, I can get rid of the crossover distortion completely, and the current is not going up yet. So this is the sweet spot, I would say. I would turn it up slightly more, so I'm sure we don't have that distortion. But I'm looking at the current, that it's not getting out of hand. As you can see, the current has gone up slightly. The crossover distortion, let's get it nice. The crossover distortion has been eliminated completely. So I think we're set for the next stage, and that is hooking up a speaker to the output and see what we've got so far. I added a couple of heat sinks to the power transistors to make sure that as I add a low impedance load to the output of this amplifier, the high current going through these transistors will not damage them. So before connecting a speaker to the output of the amplifier, it's good practice to check the DC voltage at the output. Speakers are not built to handle large DC voltages. So, well, in this case, it's a maximum of 6 volts, and that will not harm the speaker. In any case, it's a fairly budget speaker, so. Okay, well, let's connect it and see what we've got. I'll put a 1 kilohertz signal to it. Oh. Well, that's not good, and the current is rocketing sky high. So let's turn it off again. I think we are encountering the next problem. With each next step, we've got another issue to fix. Let's put this aside. I've got a 4 ohm load that could mimic the speaker, but it doesn't have the noise. So the way to go forward and find the issue causing this problem is to switch on the oscilloscope and probe at different parts of the circuit to see if we can spot where this problem originates. So I disconnect the oscilloscope at the output. So let's hook up this 4 ohm load. We've got a high current. Well, not high enough to damage these output transistors. Let's see what the output looks like. Well, this has nothing to do with a sine wave. Let's see what the output of the op amp looks like. Well, not good. Let's see what the output of the first stage of the op amp looks like. Well, that looks like a sine wave, but not in the right way. As you can see, it's not level. So that makes me think this is a power supply issue, as the sine wave is reproduced nicely. Let's take a look at the reference voltage. This is not good. This should be a level, stable 6 volt DC, and it's clearly not. Let's turn over to a DC. Well, this should be a stable 6 volt. As you can see, it's clearly not. So I would say the issue is with this reference voltage. Let's take a look at the supply voltage. Oh, that's also not good. So I think we've identified the issue. But why is this happening? Well, let's take a look at the schematics and figure out what's going on. Issue comes up as soon as I connect the 4 ohm speaker or the 4 ohm dummy load to the output of the amplifier. We could see on the digital multimeter that it draws a lot of current instantly. And this has to be provided by the output stage of this amplifier. But it looks like the power supply is not able to deliver this large amount of AC current to this output stage, as the signal looks like to travel back into the power rail. As the power rail of 12 volts is also the source for this reference voltage, this 6 volt will go up and down with this 12 volt going up and down, causing this reference voltage to be unusable and pushing this amplifier into, well, chaos. Fortunately, there is a solution by placing an extra capacitor in the power rail. A capacitor can be seen as a small local power supply, like a battery. It can accommodate large swings in the AC signal in the output stage by delivering the current when needed instantly, when the power supply is not able to react that quickly. Let's try it on the breadboard and see how this works out. So as you can see on the oscilloscope, there's a good signal at the output of the amplifier. Let's put on the dummy load, the dummy 4 ohm load. Well, the signal is all garbled as we expect it to be. Let's place a 2200 microfarad capacitor right next to the output transistors, like so. Well, that's a little improvement. Let's take another one. So we've got 2 capacitors at the output stage. Right, that's okay, that's a nice signal. Maybe if I take one out and I stabilize the voltage divider to get a stable voltage reference, maybe that's a better solution. Let's check what's going to happen here. Also a nice solution. I think I like this better. One to stabilize the voltage divider. So I think that's a good place where stabilization is necessary. So I keep one here. I think I'm good with this solution. Let's take off this dummy load. So let's try it with the speaker and see if we've got sound. Maybe turn down the volume a bit. All right, something like this. Yeah. Let's try some different frequencies. It's a bit loud. Well, looking kind of nice. I think we're ready for the next stage, and that could be a lot of fun. So such a small amplifier with rather small speakers shall not be known for its low end. So maybe we can add a feature to boost low frequencies when we feel like it. First, let's take a look at the frequency response of the current situation. I have my function generator in sweep mode. Let's hook up the oscilloscope. All right, so this is the image. It starts at 50 Hertz over here, and it sweeps up to 500 Hertz over here. As you can see, it's kind of flat response. All frequencies are equally amplified in this amplifier. Let's turn up the sweep. I'm at 500 Hertz at the moment. This is 1 kilohertz. This is 10 kilohertz. And this is 20 kilohertz. Well, the start jumped to the center of the oscilloscope. But as you can see, it's quite a flat response, so that's nice. Let's put it back to 500 Hertz, so we can see a nice picture of the low end. So let's see if we can add some tone control to boost the low frequencies. So the best place to position a tone control in an amplifier would be where the level of signals is still low. So that would be at this part of the circuit. Let's take a look what we could do at this first op-amp. As we saw earlier, the gain of an op-amp is given by the input resistor and the feedback resistor, R2, R1. The gain in this case is R2 over R1. In my amplifier, that would be 10K over 3.3 is a gain of 3. Wouldn't it be nice if we had a second path with a different value resistor, like 5 times R2, that would give a gain of 3 times 5 is 15. So we could have for some signals or some frequencies a gain of 3, and for low frequency signals we could have a gain of 15. That would result in the bass boost we are looking for. The only thing we need is to split the signal in high frequencies going through the low gain part of the circuit and low frequencies going through the high gain part of the circuit. So the way to do that is to place a capacitor. As we know, the capacitor blocks low frequencies and let high frequencies pass. So if we choose the right value for this capacitor, we can let the high frequencies go through this part of the circuit and the low frequencies to the higher gain path of the circuit. So I think it would be nice if the tone control is adjustable. The way to do this is to add a variable resistor or a potentiometer. I think the way that it has the least impact on the volume overall is to place the variable resistor over the capacitor. So let's place this circuit on the breadboard and see how it turns out. So I updated the schematic once again. I put in this tone control circuit in the first stage of the amplifier. As you can see, the path for the high frequency signals and the path with a higher gain for the low frequency signals. And of course the variable resistor over the capacitor to control the tone adjustment that's taking place in this circuit. So let's take a look at the breadboard and see how it turns out in real life. So I put the tone control on the breadboard. As you can see, it consists of 2 resistors, a capacitor of 47 nanofarads and a variable resistor or potentiometer. Okay, so let's take a look how this turns out on the oscilloscope. Let's turn it on. So as you can see, I got the sweep function on. This is the flat response. It starts at the center and it goes from 50 Hertz to 500 Hertz. Let's see what happens if I turn up the tone control or the bass boost. You can see all levels are amplified a bit more, but the low frequencies are definitely amplified more. So let's turn it down again. Let's see what happens if I put the sweep up to 10 kilohertz. This is 1 kilohertz. Well, let's take 5 kilohertz. Let's see how that looks. I'll turn up the bass boost. Wow. You see the mid and higher frequencies more or less stay the same, but the bass is definitely amplified a lot more. So that is exactly what we were aiming for. Okay, I turn it down again. As you can see, the gain in the higher frequencies doesn't change a lot. Only the low frequencies are affected by this tone control. So it looks very nice. Okay, so let's take it to the next step and put some real audio on it and see how this amplifier performs. So I connected this music player to the audio amplifier. And I also changed this cable for the tone control, as the twisted pair introduced too much noise on the output signal. I swapped it for this shielded cable. In general, noise is quite a problem in such a setup. You better make sure these wiring and traces are kept very short to have the best output signal. So let's hook up the speaker and let's play some music. Let's try the tone control. You can clearly hear a difference, and the overall volume doesn't change that much. Well, it sounds okay, but let's put on a real speaker and see how it sounds. All right. Okay, here we go. Sounds pretty good. Let's try the tone control. Stars above shining bright. I feel the rhythm's gonna be all night. That's the sweet soul. Well, that sounded really great for such a experimental setup on the breadboard. And the bass control did its job. It really gave the low end the extra boost these small speakers can use. It's really nice to be able to adjust this low end to your liking. So I'm quite happy with the result so far. Well, I've decided to put this amplifier to real use in my workshop. To make it work properly and to cut down on the noise, I mounted it on a printed circuit board. As you can see, I've got 4 of them right here. It doesn't have to be expensive. I think I paid less than 15 euros for this. To get the best sound quality out of a PCB, there are a few design principles one can keep in mind. Maybe we should talk about that a little bit. First, it's recommended to isolate low-level input signals as much as possible from other signals and power traces. They are the most vulnerable to interference from other signals or power lines. Not only you have to isolate, but also keep the traces short to minimize the risk of picking up noise. So this is the part where these signals come in. And this section is the input section where the amplification takes place. These are the positions for the 2 op amps, for the left channel and the right channel. And they're isolated from the power supply section, where the filtering of the incoming power supply is done and the reference voltage is created and stabilized. You see positions for the caps to do this. And here is the output section. As you can see, it has wider traces to accommodate for larger currents and lower resistance. This is where the 4 output transistors for the right channel, left channel are positioned, and the output caps, of course, the buffer caps, they are located as close as possible to these power transistors. I had some space left on the PCB, so I drew some optional components in case I want to add a filter or a capacitor later. I will show you on the schematic in a moment. So one of the great advantages of using a PCB is the ability to use a ground plane. That's this side of the PCB. It's the most effective way to ensure solid grounding and minimize distortion in the return path. I only had to route a couple of crossing traces through it, so that's okay. So I'm very happy with that. Now you could try building this on a variboard or strip board and soldering everything by hand, but trust me, that's asking for trouble. I've been down that road and it's easy to make mistakes. Low-level signals are hard to isolate from power traces, and it will lead to crosstalk and distortion. Plus, without masking of the traces, leftover flux or tiny solder particles can use unwanted currents and noise. So, in the long run, you will be better off with a printed circuit board. Okay, so I've updated the schematic one last time. So if you're thinking of building an audio amplifier yourself, this could be a solid starting point for your project. Let me show you the optional components I put in. So I added an extra optional cap here, 100 nanofarad. I've added some extra caps here, optional, to buffer the reference voltage near the op-amps. And I've added an optional resistor here that can be placed if the capacitive load is too large to be handled by the output of the op-amp. If the amplifier is pushed to the max, the output signal can get distorted. It sounds like some kind of oscillation is going on, and by putting in a very low value resistor, the output stage can be decoupled from the op-amp stage and the problem will disappear. So that's an optional one. I've got an optional filter at the output to filter out high frequency noise. It is outside the range of the human ear, but these frequencies sometimes can create artifacts in the audio range. So one could take some measures to reduce that. I've also put in the option for a discharge resistor here. On startup, a voltage can be induced in this part of the circuit through the capacitor. Speakers are not built for DC voltages, so by putting in a discharge resistor, it can help to get rid of the voltage. But in my case, with these low voltages, I don't know if that's necessary. There may be a plopping sound on powering on the amp, but I don't think that's harmful or interfere with the audio signal. But I had space left, so I put it on the PCB anyway. Oh, and of course, I put in this variable resistor as a volume controller. So that's the final circuit, I guess. Let's take a look how this turned out in real life. So this is the final build of the amplifier. I created the casing for it on my 3D printer, and I put in the printed circuit board as well as the switch mode power supply. There's room left for a Bluetooth receiver I'm planning to add later on. These are the control knobs, this for the bass boost and the volume. I added a third one, and it's a selector to select between line input and the Bluetooth receiver when it's installed. For the wiring, I used all shielded cables. This is the best way to protect your low-level signals from external noise. I've been extra careful to connect the ground wire or the shielding wire only to one side. It is strongly recommended to avoid ground loops, as this can lead to noise in your audio output. So let's take a quick look at the printed circuit board. This is the input and amplification section. Here you see the two op-amps, one for the left channel, one for the right channel. It is well separated from the output stage and the power supply section to avoid interference. So this is the power supply section as discussed earlier, and these are the output channels, left and right. I mounted the custom-made heatsink on the power transistors. It's just a strip of aluminium I bent in the way to fit the transistors. So here you probably will recognize the emitter resistors and the output caps. And this leads to the speaker terminals, as you can see. I hooked up a probe for the oscilloscope as well, so let's take a look and let's take a listen to the final version of this amplifier.
underneath the moonlight of a corner ride.
Sounds really great. As you can see, there's a lot less noise on the signal compared to the test setup on the breadboard. Let's check the bass boost. So now it's at its minimum. This is all the way up. And this is all the way down. I'm not sure if my microphone will pick up all these low frequencies very good. But let me tell you that there's a significant difference to be heard. Very nice how this turned out. Okay, well, I think that wraps it up. I hope you enjoyed it, and I see you guys in the next video.